Okay, we're going to do a little graphical exercise again. Get a full screen coming in from the cold. All right, knock the hair down, ready to go. Very early morning here. So I'm going to just pose a quick question. Intentionally not putting any numbers down and try to work from just what you're looking at. What would happen if you multiplied these two lines together? What kind of graph would we create? And you're just looking in general, just in general here. And we'll look at some of the salient characteristics again of what is created. All right, so you can pause the video. And I'm going to try to remember to say pause. Right, and I'm just going to continue through this process. So let's call this one Y1. Let's call this Y2. Now, what do we do when we have a Y equals? Well, what do we do when we have something like 2x squared plus 5x minus 7? Now, we have inputs giving us outputs, and those Y values are expressed visually. Right? They're expressed as how far value is vertically from the x-axis. So this is a height of 0. So therefore, what would, well, let's see, I guess I could get out that far. What would an input in this vicinity get us? Well, it would get us a vertical, and I'll do another vertical here for that. And so I would be multiplying this value times that value. What can we say? Well, they're both positive. So I'm going to get a positive answer. The size, not looking at size at the moment, yeah, but we're going to get a positive answer, and let's just go with kind of the scale that we have here. Although, I mean, this could be 1,000th times 1,000th, and well, 2,000th, and you know, we might be very low, but we've got a positive outcome. So let's just go just in general and say that that positive outcome yields this location as a vertical. Okay. Well, what would happen if I went to the right? Well, it looks to me like each of those Y values is now bigger than the last one. And therefore, the product should be bigger. Maybe significantly so. Eventually, as I move towards infinity, 1,000,000,000 times 1,000,000,000, you're accelerating, you're really getting up there. So we can assume that it, on the right, its end behavior is getting larger and larger and larger, pretty quickly too. So now let's back up and go in the other direction, pause. See what seems to be the most important number in that vicinity. So you're pausing the video, thinking about it. I'm just going to continue on. It's right here. All right, for this first function, Y1, that's a 0. And if we're going to multiply that times this altitude, well, I got a feeling at that instant, we'll call it coordinate B. We'll just leave it coordinate B. I'm going to get a 0. Pause the video. What happens as I move to the right? Well, I'm just going to keep talking. These linear values, these Y values for Y1 appear to be negative now. And that started right here. Right there, that Y value, tiny as it is, and it's going to be really tiny. And what happens when we multiply something? Let's give this a value now. Let's say that this is 5 units high. Well, a little bit less than 5 because we're to the left of that now. We're to the left of coordinate B. Well, right in here, I've got numbers like negative 0.00003, things like that. I've got numbers like that in this vicinity. And if I'm multiplying them times something that is, 100 times bigger, well, 100 times bigger simply just puts a 1. Well, that's 10 times bigger, so 100 times bigger. But the bottom line is you've got a very small negative number. So you're not changing much, but you sure as heck changing in the negative direction. All right, so pause the video again. Well, I certainly have a 0, 0 right there. So at 0, this might give me some little bigger negative number, a little smaller one here, but really this is the one that's important. So I do have a y-intercept. Right, it's similar, you know, it's just going to be a little bigger negative number than before, right? And at some point here, seems like there's a moment where the negative and the positive have the same magnitude. And that moment creates kind of a fictitious square area. Because that's a line, and that's a line. That gives us a negative area in this instance. That's square area. Let's just look at a couple of numbers that add up to 6. 0 and 6, 1 and 5, 2 and 4, 3 and 3, 4 and 2, 5 and 1. That's enough. Let's multiply these two numbers. 6 times 0. Geez, that appears to get me an area of 0. 1 times 5, 5. 2 times 4, 8. 3 times 3, 9. 4 times 2, 8. 5 times 1, 5. Ooh, there seems to be a maximum area when a value gets multiplied times itself. If those two numbers add up to a constant, we get a maximum area. Well, two side lengths that are the same maybe give us a maximum negative area. Sure looks possible. Why? It's just the numerics. So pause the video and ask yourself, what happens when y2 equals 0? Well, 0 times anything gets you back to 0. And that's location A. And this minimum location, I hope you're starting to see what's coming about here. This minimum location we'll call C, right? So let's just say that that's coordinate A, coordinate C, coordinate B. And what's going to happen as we move further and further to the left? Negative times a negative, negative times a negative. I think a negative times a negative gets me a positive. And I think we're off to the races. Boom. Boom. That's the kind of shape I'm going to get from my graph. So let's look at some rectangular situations that have, evolved historically, one concept leading to another. Let's just look at a rectangle. I put some notes over here so I remember to say the things I want to say. Maybe not the best scale, 3 to 5. All right, maybe that's not the best drawing, so let's get a little better drawing. And let's see if we can, well, I don't want to lose this completely. But let's see if I can work it out right here. So that's 3, that's more like a 5. And I've got a 3 by 5 rectangle, 15 units of area, columns, 5 across, 3, 2, I'm not going to show those. All right, but 3 times 5 is 15, cut to the chase. Well, it's also true that a 4 times a 4 minus 1 gets us 15 units of area on the left and 15 units of area on the right. Just some manipulations, just some drawings. Okay. And 4 seems to be a very important number in connection with 3 and 5. 3, 4, 5. It seems to situate itself right between those other two numbers. And, squares, they hold a very important position in the set of quadratics, four-sided figures called rectangles. Seems like a square is, for some reason, seems to stand alone. It's the only rectangle that has the same side lengths. There's a lot of rectangles out there. Yeah. All right, so now it's time to, I think, give these linear functions a name. Well, why don't we call that one x minus 2? And why don't we call this one, that's positive. So let's call that x plus 8. And let's see what we get if we multiply that out. Well, let's multiply 2 times 3 to get 6. Let's call the number, well, let's make it 3 times 5 is 15. Let's go there. And I know 3 is 1 plus 2. Oh, we'll do 4. Nah, 3 plus 4. No, let's do 7. All right, so 21. You can tell I'm doing this on the fly. So let's go 3 plus 4. I think we better get 21. All right, so we've got an algebra 1 moment here. I think I have 1 3. I think I have 1 4. I think I have 2 3s. And I think I have 2 4s. And I think 7 and 14 adds up to 21. So if you do that here, I think I have x squared plus 8x minus 2x minus 16. And those are like terms. So I think I have x squared plus 6x minus 16. I think I can put a number in either side and get the same answer. So let's put the number 3 in. 3 minus 2, 1. 3 plus 8, 11. 1 times 11 is 11. And I put the number 3 in. That's 9 plus 18 minus 16. Well, 18 minus 16 is 2, and 9 plus 2 is 11. Seems to be the same calculation expressed differently. I think this one is just like our 3 by 5 rectangle. I think this one can be expressed by evening off the side lengths. And so I have minus 2 and 8, which adds up to 6. And if I cut that in half, I get a 2. So 6 divided by 2 is 3. I think I can do one of these. X plus 3, x plus 3. Let me see if I can sneak that in over here. And I think if I multiply that out, I get x squared plus 6x plus 9. And I know what I get over here. I get x squared plus 6x minus 16. I think I can come over here and subtract 25. I think 9 minus 25 now matches up with that. And so it seems like I can express x minus 2 times x plus 8 equals parentheses x plus 3 squared, something times itself, minus 25. Now, why might that be helpful? Well, each side of this equation tells me something different. This side tells me that if I use the number 2 for an input for x, then the product becomes 0. And if I use the number negative 8, and I plug negative 8 in, the product is 0. And I think that's going to happen over here too. 2 plus 3 is 5. 5 squared, 25 minus 25. Yup. A 2 gets me a 0, and so will negative 8. Now, it's interesting. There's a number that sits between 2 and negative 8. Pause the video and see if you can find it. And if you said 3, negative 3, excuse me, If you said -3, you'd be right. And -3 plus 3 is 0. And 0 squared is a minimum. You can try any other number you want. And if you don't use 0 times 0, you're getting a bigger answer for area. I don't care if you use a positive or a negative. You square a positive, you get a positive. You square a negative, you get a positive. But when you square 0, and what number are we squaring over here when we plug in -3? I wonder what number. -3 plus 3. Oh, we're creating the minimum value. And in this case, it's -25. And then we can come back over here. We can say, oh, I can tell you what B is now. If this Y altitude, this one right here, came from X minus 2, and this Y value came from X, this Y from here to here came from X plus 8, that function X plus 8, this one X minus 2. And if I multiplied those two things together, I've been kind of analyzing it over here. Okay. Then I start to get this shape, and I know that at +2 I get a 0. I now know that at -8 I get a 0, and I now know at -3 I get -25. I can start putting a lot of information on the board. And I can tell you what those roots are by doing inverse operations now, because making it a square, I can use an inverse operation called a square root. Now, why can't I use a square root on a 3 by 5, right? I don't think that's a square root. Why not? I don't think that's a square. So somebody hundreds of years ago must have said, hey, we can reconfigure this and solve a lot of equations pretty easily with something called completing the square. All right, which I will do for you now. But there's also a topic we'll be studying. Not only is it important to set trinomials to 0 and be able to factor, that's what we call this process, x squared plus 6x minus 16 could have been written that way, and it's a major skill at the Algebra 1 level. It's introduced early. All right, I'm not sure I would like to use the word factoring as much as books do, because what I see here is a sum and difference. I see addition and subtraction of terms that are now expressed as a product. That's what factoring is. It takes addition and subtraction expressions and then rewrites them as products. Why is it helpful to rewrite as a product? Well, you got an inverse operation for a product. You got division. You can reduce fractions with this process. That seems to be important. So where was I? I forgot. But oh yeah. Well, we also want to know when things are greater than 0. And I think we've explored that. So come back to think a little bit over here. It's a messy board now. But when is a product greater than 0? When a positive gets multiplied times a positive, then it's true. And when a negative gets multiplied by a negative, then it's true. And I think we can come over here and we can put any number bigger than 2 in. Let's put a 3 in. That gets me 1 times 11, which is a positive times a positive. And we kind of started our analysis over here. A positive times a positive. Everything to the right of this B value, that critical number, which in our case is 2. So therefore, from 2 to infinity, might as well get the interval notation in there, it was on your first worksheet, is one of our answers. And it seemed like when we had a negative times a negative, we got ourselves positives. This is the terrain of negative times negative. That's what created that. This was the positive times the positive. That's what created that. And this is where we had a positive times a negative in between. We have a positive altitude, a negative in between those two critical numbers. And so this is interval notation. And so that's negative infinity to negative 8, union 2 to infinity. Right? And that's basically showing us this and showing us this with the word or. Numbers here or here satisfy that equation. All right, we'll be practicing that the rest of the semester. All right, once we start conversations. Now, what happens if I wanted it to also be equal? Well, in middle school, you colored in those dots, and you make a bracket. Make a bracket instead of a parentheses. It's easier notation to use when you have lots of intervals that work and intervals that don't. So did I catch most everything? Yeah, except for one last thing. All right, so let's just do the fact that we created a square. Let's look at our vertex. Our vertex became -3, -25 in this instance, right? And our A term was 1, right? It was x squared plus 6x minus 16. This is times 1. So we have an A value of 1. And let's just solve this quickly. Do I have another marker? No, we better hope this one lasts. Ah, got one more. Let's hope it's got some good ink. This one's starting to die on me. So we got x plus 3 squared. That's what that's all about. Minus 25. Let's set this equal to 0. You can bring the 25 over. You can take the plus minus square root of that. And you can bring the 3 over, and you've got -3 plus minus the square root of 25, which got divided by 1. Okay, so we're going to be practicing that. Also the things we can do with completing the square. Right, so yeah, I'm not done. I'm going to continue here because this morphs into so many different topics. All right, and one thing that we're going to learn is that if you have a vertex, let's make this 4, 7, and you have an altitude of 0, and you have an A term of 2, right? Then you can just write your answers. The answer to that, without any work, you don't have to do any work, is measuring from 4, moving plus or minus, right? You got to go 7 units to get to 0, but you got to go down 7 units. And the A value is 2. So you move the negative outside, you got that, you got your roots, and you don't have to do any work. Of course, to get there, it's going to take some practice. We got to do it every day. We do it every day for about a week or 2. Yeah, just a minute or 2 every day. Most students get it. Now, what did I do? Well, let's work backwards. Let's get this back to the quadratic I started with. So here's 4. So I'm going to write x minus 4. That leaves me plus minus the square root of 7 over 2 imaginary. Let's square both sides. X squared minus 8x plus 16 is equal to, squaring this gets me 7 halves times I squared. 7 halves times I squared. Okay, see where this goes. I squared is -1, so this is really -7 halves. I can double everything over here. 2x squared minus 16x plus 32. Looks like it's equal to -7. And so I could have started with 2x squared minus 16x add 7, 39. Set that to 0. And if I complete the square, which is putting quadratics in graphing form, which isn't hard. It's a 30-second process, which we're gonna learn. And it's based on what? Minus b over 2a. Okay, so it's all based on that. All right, so let's look at that really quickly. This is a much longer video than I anticipated, but that's okay. We're on a roll. We got to get these things started at the beginning of the term. The conversation started. Ax squared plus bx plus c equals 0. Let's look at that, where the quadratic formula comes from, which I don't use much anymore. But embedded in every quadratic is a beautiful little rectangle. That's x times ax plus b. And if I had c, and I want to solve this, then I got to make that into a square. I got to even off the sides. And so to even off the sides, remember what we had before. We had x minus 2, and we had x plus 8, right? What were the two critical numbers? What made zeros? 2 and negative 8, right? Those are the two numbers. 2 and I'll put the negative 8 out here. And we divided by 2 to get negative 3. That's what we did to reconfigure this rectangle, which doesn't look like it. Looks more like a flashlight. Let's put a little rotation here, and then we can do some rotate around the x-axis stuff in calculus one. No, let's make a better rectangle as in that one. All right, so what makes a 0 here? 0. What makes ax plus b equals 0? I hope you can see minus b divided by a. Okay, so minus b divided by a gets me a 0. And that is going to yield the letter C. So if this thing becomes 0, each of these becomes C, each of these becomes C, and we have a couple of places in a parabola. I'll use a bigger than 0. Well, I think what we're looking for is right in between those two numbers. So how do you get something if you got a test score of 80 and 90? What's your average? Add them up, divide by 2. And if you add these things up and divide by 2, you get minus b over 2a. Wow. Wow. So let's just use minus b over 2a up here with the function that I just lost on the board. So I'll make a new one. So let's look at 2x squared plus 20x minus 3, and we'll just put that in graphic. So minus b over 2 times a gets me negative 5. I want that to act like 0 squared, so I write x plus 5 squared, and I already have the 2. If I multiply this out right now, I get 2x squared. 10x times 2 is 20x. 5 squared, 25 times 2 is 50. And I don't really want that 50, so I'll subtract it out of the problem because I want it to end with negative 3. Sure looks like if I put a 0 in here, I get 50 units, but I don't want 50 units. I want negative 3. I guess I better go down 53 units. But let's check it by plugging negative 5 in. So that gives me 50 minus 100 minus 3. And yes, that is true. And yes, there's our 2-to-1 ratio, which always happens at the vertex of a quadratic. How nice. So now I can look at 0. I know I got minus 5, plus or minus. I've got to move that to the other side, and I got to divide by 2. And I can get roots pretty quickly by doing this. So there's a lot that we're going to be covering this semester. We've just started. And we got so many nice things to start working on. So let's have at it. This is what I'll upload for a little homework over the weekend. And give you a worksheet, and we'll get going and hopefully make some gains. All right. So I'm going to do a 40-question worksheet, I think, something like that over the weekend. And I will do a video on each of those problems. And that's where we're at on day 3 of our new class.